In this video, we're going to learn about the concept of polar coordinates. So originally, about a few hundred years ago now, a guy named Rene Descartes came up with this idea of describing any point in a plane that you want to talk about by first specifying a reference point, and we call that the origin. And then once you have your reference point, asking yourself, how far did I move left or right? In this case, I moved 4 to the right. Then how much am I going to move up or down? In this case, I moved 3 up. And then we describe this location, this point here, as 4, 3. And so by using this method, we can describe any point we want to by giving these two numbers here. Well, it turns out that even though that's an amazing breakthrough and allowed us to connect algebra and geometry, even though we had that, there are some problems that using this system end up becoming very complicated. And it turns out there's another system that will make some problems significantly easier, and that's going to be called polar coordinates. So we're still going to have a reference point here, except now instead of calling it the origin, we're going to call it the pole. And then what we're going to do to describe these different points here is we're not going to say how far left, right, up, or down did you go. We're going to first, how far is it to go straight there? And if I try to imagine it's the same point here, 4, 3, then if I want to say what the distance is, well, we can calculate this here. By Pythagorean Theorem, square root of 4 squared plus 3 squared, we're going to get 5 here. So we're going to go a distance of 5 to the right, or not to the right necessarily, 5 in this weird direction here. And so we need to specify what that direction is. And so what we're going to do is we're going to come up with an angle, and we're going to refer to the positive x-axis as our starting point for our angles. So that would be like 0 degrees. And then we're going to say, well, how much did you have to turn here to get to that direction to go 5 units there? And we can do that using trigonometry here. Right, we can say, okay, tangent of this angle, say theta here. Tangent theta is y over x. So in this case, theta would be tangent inverse of 3/4. So what we can then do is, instead of just describing it as left, right, up, and down, we're going to describe it as how far do you move and which direction do you move. And as I said, it's going to make some problems turn out to be significantly easier. Let me give a rough idea here of where that might come up. If we had a regular, what's it called, Cartesian coordinates, named after Descartes, if you want to deal with problems that involve rectangles, they're going to be pretty convenient here. For example, I can describe this rectangle as x has to be between 0 and 4, and y has to be between 1 and 3. On the other hand, if I had, I don't know, how about a piece of a circle here? So I have a little sliver of a circle. That would be incredibly difficult to describe using x and y. Right? There's no nice equation that's going to give me all of that shape right there. So when you're using Cartesian coordinates, also called rectangular coordinates, it's really useful for describing rectangles and things like that, but it is not good for looking at circles and things that are curved. However, if I want to do polar coordinates and I want to describe a shape like this, I can say it's all the points whose distance r is between 0 and say 5 or something like that. And then I want only the points whose angle is between 2 pi over 3 and 5 pi over 6. And that simple description would describe that weird part of a circle there. On the other hand, if you tried to draw a rectangle in polar coordinates, that would be incredibly difficult to describe using using r and theta, but would be really easy to describe using x and y. So we're just learning a new way of describing points and giving numbers to them. And it's just that some problems, the x and y are going to be easier to solve, and some problems, the r and theta, are going to be easier to solve. And so it's important for us to be able to go back and forth. And in this video, we're just concerning with what they are and how do we convert back and forth. Well, let me draw the picture one more time here. If I take a random triangle here, and I want x to the right and y up, and my hypotenuse is how far I'm traveling is r, then I can get the following equations here. If I call this angle theta, then x is equal to r cosine theta, y is equal to r sine theta. So that's a relationship between x, y, r, and theta. Can allow you to convert from one to the other. On the other hand, if you want to convert in the other direction, you can solve, and by Pythagorean Theorem, r is equal to the square root of x squared plus y squared, and by trigonometry, tangent theta is equal to y over x. Now let's actually use those to convert some points here. So I go ahead and I have looking at the point -3, 3. So I'm at this point right here. I'm going to use the equations on the right to convert this here. So I'd have r is the square root of x squared plus y squared. So -3 squared plus 3 squared. It's the square root of 18, which you can simplify that. It'd be 3 root 2. And then I need to have the other equation, tangent theta is y over x, so 3 over -3. So tangent theta is -1. Now I want to point out something here. The equation was that tangent theta is y over x. It was not that theta is tangent inverse of y over x. And the reason why that's the case is if you do tangent inverse, it's not always going to be the right answer. We've learned in trigonometry that if you do tangent inverse, the answer is always going to be in either quadrant 1 or quadrant 4. The answer is between -90 degrees and +90 degrees. However, if we look at the point -3, 3 over here, that's in quadrant 2. So you have to be careful. Anytime you have a point in quadrant 2 or quadrant 3, just doing inverse tangent is not going to be enough. But well, we can then look at our triangle there, and we can see that theta is going to be at 3 pi over 4. And so the point in polar coordinates would be the r is 3 root 2, and the angle is 3 pi over 4. So that is our way of describing that point there. Now to go the other direction, here we have a point that's currently written in Cartesian coordinates, and now we're going to convert it to polar. For this one, we're going to go ahead and use the formulas x is r cosine, y is r sine. It's maybe a little bit easier here. So r cosine, y is r sine. And then you have to know your values of your trig functions. Cosine of 3 pi over 4 would be negative root 2 over 2. And sine would be positive root 2 over 2. So we're going to get a -3 root 2 and a positive 3 root 2, which means the point in Cartesian coordinates is this point right here. So you see you can convert points back and forth, whichever is more convenient for a problem that you might have in the future. But even more than that, we can also convert equations, and this is where things really come important, because if you look at x squared plus y squared equals 16, that is not a function, right? If you graph it, you get a circle, it fails the vertical line test, and when you're taking like calculus classes and stuff, the fact that it's not a function can be a problem. However, what I can do is I can use these equations up here, X squared plus y squared is going to be the same as r squared. And then square root both sides, and we get a much simpler equation, r equal to 4. And you can use that in calculus instead and have a much easier time with the problem. Right? If you had tried to solve for, say, y in terms of x for calculus, you'd have this messy expression. Whereas if you just have r equal to 4, it'll make life easier. Similarly, we can go the other direction. We can convert something that is currently in polar into Cartesian. This one is one that's fairly common, and there's a little trick that you need to do, because if you look at the equations to convert to x and y here, there is no just sign. There's an r sign, there's an r cosine, but there's no formula that just has sign. But what we can do is we can go ahead and multiply both sides by r. And once you do that, the r sine theta, that will go ahead and become y. And the r squared on the left side becomes x squared plus y squared. Now this right here is perfectly fine. You have a Cartesian coordinate equation. But if you wanted to know what your shape was, because it might be important to graph it, what you would do is you'd have to go ahead and do a little bit of completing the square here, adding 4 to both sides. And then once you realize this, you're going to have a circle whose center is 0, 2, and whose radius is 2. So now we know that r equals 4 sine theta is going to be a circle here. So again, this video, we're just focusing on converting back and forth. We're not actually using it to solve any further problems, but in later classes, you will use this to solve problems. And it's important to get the basics down now.